2.1, the fundamental counting principle. So let's do a mini investigation. When planning a trip from Niagara Falls to Ottawa, Betty wants to stop in Toronto. Okay, so we're going from Niagara Falls all the way to the Ottawa. She's going to stop in Toronto and Belleville on the way. Okay, so we know we're going to go from Niagara Falls to Toronto to Belleville to Ottawa. Suppose there are 2 routes that Betty can take from Niagara Falls to Toronto. Okay, so she starts in Niagara Falls and she can take Toronto Route 1 or Toronto Route 2. Now there's 3 different routes she can take from Toronto to Belleville. So Belleville 1, first route, Belleville second route, Belleville third route, or Belleville first route, second route, third route. And 2 different routes that she can take from Belleville to Ottawa. So Ottawa 1, Ottawa 2. 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 So, create a tree diagram, which we already did, to show the different routes that Betty can take to get from Niagara Falls to Ottawa, and then list the total number of routes. So, instead of the list, we're going to state. So the total number of routes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 routes that she can take. Now, when we're talking about the fundamental counting principle, we're going to be able to do this algebraically. So we focus on tree diagrams in order to get that visual, but now we're going to do this algebraically. So the rule is, if a task or process is made up of stages with separate choices, okay, so M, N, P, and so on, the total number of choices, what we do is we multiply them. So M is the number of choices for stage 1. So that would be from up here, going from Niagara Falls to Toronto. And then N is the number of choices for stage 2. That'd be going from Toronto to Belleville. And then stage 3, in this case, would be Belleville to Ottawa. Okay? And you can extrapolate and you can tack on more and more stages if needed. Okay? And the buzzword that we're looking for is the word and. Okay? This is happening, and this is happening, and this is happening. I'm going to give an example of that. So, for this one, we're going to do the Toronto Route 1, then the Belleville Route 1, and then the Ottawa Route 1. And these are all happening in order to get me from Niagara Falls to Ottawa. Okay? Or Toronto 1, Belleville 1, Ottawa Route 2. Okay? But it's like I have to take this route and this route and this route. All of those have to be done in order to get from Niagara Falls to Ottawa. So that's why we say simultaneously. It's happening at the same time under the scope of that one event. Okay? So the event is Niagara Falls to Ottawa, but our mini events are Niagara Falls to Toronto, then Toronto to Belleville, then Belleville to Ottawa. Okay, so simply put, we're going to use the fundamental counting principle to solve for the total number of routes. Okay, so the total number of routes are going to be, well, Niagara Falls to Toronto has 2 routes, Toronto to Belleville has 3 routes, and Belleville to Ottawa has 2 routes. So if we go 2 times 3 times 2, we're going to get that 12. Okay, and if you notice, these match. Okay, let's talk about the underline method. So when using, this is used when calculating the number of ways that items can be ordered, dependent on the number of items that you wish to order. So what we're going to do is we're going to draw an underline for each of the number of items that you wish to order. Then what we're going to do is we're going to fill in each underline with the number of items available. And this may change dependent on whether or not you can use or reuse the items, aka replacement, non-replacement. Okay, so you roll a standard 6-sided die. How many outcomes are possible with 2 rolls? So we're going to have 2 underlined. This is going to be the first roll. This is going to be the second roll. So on a 6-sided die, you can roll 6 different outcomes. The numbers, obviously the universal set is numbers 1 to 6. And then on the second roll, you can roll another 6. So there are 36 different ways that you can roll this die 2 times. But 3 rolls, we would do 3 underline, the first, the second, and the third. So 6 times 6 times 6. Or we can write this as 6 cubed, or we can actually solve for this by putting it into our calculators. Let's do 16. Okay. Example 3. A 4-digit code must be created for a padlock from the numbers 0 to 9. So the numbers 0 to 9 are the 1-digit numbers. There's actually 10 of them because you have to include that 0. So how many different numbers are possible? So if it's a 4-digit code, we're talking about the first digit, the second digit, the third digit, and the fourth digit. And you can label these if you need to in your head, but you don't have to label what each of these underlines means. That's okay. So a 4-digit code, there's no restrictions because it doesn't say that it has to be a certain number or that numbers can't be reused. So this is just in general a 4-digit code. So there's 10 options to choose a number for the first digit, and 10 to choose a number for the second, and 10 and 10 for the third and the fourth. So this is 10 to the 4, or it's 1000. There's going to be 1,000 4-digit codes that can be created for a padlock. Okay, with numbers 0 to 9. Okay, so that's all with no restrictions. Now let's take a look at restrictions. So we're going to talk about without replacement. Okay, so this is non-replacement. What ends up happening is each time one item is slotted into a position, the number of items then decreases by that 1. So we're going to reduce the next number by 1. So a class of 20 students are selecting 3 students to go to a seminar. Okay, 1 as a speaker, 1 as a videographer, and 1 to take notes. How many ways could 3 students be selected for these 3 positions? Okay, so originally you have 20 people in the classroom, you have 20 options. But as soon as you choose one of those students in order to be a speaker, then you only have 19 left. So there's 19 ways that you can choose a videographer. And then when you slot in the videographer, there's only going to be 18 ways that you can choose a note taker. So there's actually 6,840 ways. Double checking that. Yep. To choose 3 individuals to go to this seminar. Okay, let's keep going. A band has 5 songs that they will be playing at the next school dance. How many different ways and how many different orders can the band play all 5 songs? So first song, second song, third song, fourth song, fifth song. The assumption is, especially with like DJs, is that they're not replaying songs. So you have 5 songs to choose from for the first song. But once you play that one, we cannot replay it. So then there's 4 songs to choose from for the second song. Once you play that song, you can't replay it. Okay, 3, likewise 2, and 1. Okay, most of the time I ask you just for the equation. If you do want to know the total number, it's 120. So there's 120 ways that the band can play all 5 songs. Okay. So now what if we have 5 songs, but we only have time for 3 of them? Okay. And obviously they're going to be different songs. So there's no replacement of that song back into the mix. So this one would simply be 5 times 4 times 3, and then we stop. So there's 60 different ways to order 3 out of the 5 songs. Okay, example 6. Until 1997, most license plates for cars in Ontario had 3 numbers, number, followed by 3 letters. Okay, calculate the number of possible license plates if there are no restrictions. What that means, so when there are no restrictions, it means that all of the numbers and letters can go back into the groove, and you can have an awkward, like for example, a license plate as 000 AAA. For an example, like you can have repeats. So for focusing on numbers are out of 10, okay? Because they're the numbers 0 to 9. So I get 10 times 10 times 10 for the numbers. And this is followed by 3 letters, which I get 26. So 26, 26, 26. If you want to write this as 10 to the 3 times 26 to the 3, that's okay too. Okay, so again, calculate the number of possible license plates if 3 letters must only be O, N, and T, and it allows duplicates of these letters. So there are no restrictions on the numbers. So for the numbers, N, we still have 10, 10, 10. Now there's a restriction on the letters, okay? So O, N, T are only 3 letters, but we can duplicate them. So we can have O, 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 N, 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 T, 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 okay? So we actually put these back in the mix. So we're going to have 3 times 3 times 3, okay? With those 3 options, O, N, T, O, N, T, O, N, T. 3 options for each. Okay, now, how many possible license plates are there if 3 letters must be ONT, but this time no duplicates? So again, there's no restriction on the numbers. The numbers can be 0 to 9 and they can repeat. Now, for the first ONT, there are 3 options. But once you use one of those letters, let's pretend we use O, we only have 2 options left. Say, for example, we use N, we only have 1 option left. Okay. You can write these as 10 to the 3 times 3 to the 3. And you can write this as 10 to the 3 times, it would be times 3 times 2. Okay, you should put in the times 1 just to show that you have taken into account that last letter. Okay, now if neither the letters nor the numbers have duplicates. So you got to think, we're not building this off of the ONT. We're going back up to the original situation and we're building, like we're not building, so we're just taking it from the original. So if we cannot repeat numbers, there's 10 possible numbers. Once you use one of them, there's 9 left to choose from. And then once you use one more, there's only 8 numbers left. Okay, and likewise, we would have 26. Now we use one of the letters. We have 25 letters left, and now we use one of the letters, and now we have 24.